spectrum is to identify the particle. What is the spectrum of It's somehow obvious to me we use this expression. I'm sorry if it wasn't clear. Huh?
It's used a lot in particle stimulated spectrum.
Right. But I think I was clear. You don't. What I said later. You don't have to compute the masses in some cases when they mix. Just look at the matrix and find the conditions. So it should be clear, right? You want to identify the states. Do you think you need more time because of that? Is that wasn't clear? You should have written them.
No.
Well, that's what.
If that's the case, it's
No, you can't. I mean, okay. I may have to make a break and get some water in the fountain in the world. So let's see how it goes. No questions. So this is it. We are building the standard model, we said, right? The electroweak part, I'm sorry. The electroweak part, which we said is SU2 L cross U1 period. So this is the first step. We identified the gauge structure. It's almost all we need. Of course, we know who the protagonists are. We have to specify the matter, which is quarks and leptons. And the left and the quarks we said are the doublets. And the right-handed one are singlets. Remember we said U1 has to be there because I need to split the charges of quarks and leptons. They're completely different from each other. They couldn't work in SU2. In SU2, everybody had the same charge and, of course, the wrong charge. That's the way it works. The left-right asymmetric structure is parity violation. And you see I keep emphasizing maximal. Maximal means that these are singlets. If it was not maximal, I don't know what I would even, that would be complicated. Parity conservation would mean these are doublets. Maximal is a singlet. Which effectively means we'll reproduce it in a second. Well, it will be clear in a second. And you will figure out, okay, here, I could have put something. But the standard model is a theory of observed. It's a minimal structure of observed particles, so I'm not allowed to put the states that nobody have ever seen. This is called the right-handed neutrino. We'll talk a lot about it. So it's all specified by the covariant derivative. This is my gauge structure, which is d mu minus Ig dA A mu A minus I G prime. So this is a coupling constant G. The generator I called Y/2 for some silly reason. And the gauge field of U1 I call B. When exhaust state I call it B. And TA, what it means here is that TA is the TA is sigma A/2, and here we said TA 0. All I have to do is write my Lagrangian, which is I sum over all the fermions I can write this sum, but you understand. And the fermions stand for all these fields. By the way, how many of them there are? Do the counting while I'm writing. Tell me how many fields there are. The number will sometimes be amusing. you count it? Someone? No? This field.
There seem to be 7.
7?
Seem to be.
1, 2, 3, 4, 5, 6, 7. Yeah, there seem to be 7, but you said seem to be.
Yeah.
You didn't say there are 7.
Yeah, there seem to be 7.
So you're saying that U is like an 3 column vector, like up, down.
Yeah, of course, they carry color. Oh, you, sorry.
Okay.
No, these are my states here.
You're not assuming like 3
No,
families.
no.
Only one family.
No, this is the better, this is what the universe is made of, okay?
No, but
There are no other families for the time being, we'll come to it.
okay.
The understanding, you know, if you want to have a deeper understanding, you start with one family, you really make sure that you have the nitty-gritty of that. Then you do 2 families, because you can write analytically what happens. It's very important to have this graph. And then if you have to live with 3 families that you and I have to, it gets messy with 3 families, as you know. A little bit, there are certain things, so it's good to have to. And in a 2-family case, you will see the understanding of mixing is deeper. No, it's just to remember that these guys do carry color. It's irrelevant because I'm studying what happens when I go from here to here, so color. There is a color index here, which I'm hiding. Red, yellow, blue. I don't know what colors you like. So there are actually 15 states. We'll see why this number becomes important, not in the standard model. See, if I want to unify them, I have to know how many particles I have. But here it's irrelevant. I treat them. Quarks are quarks, and leptons are leptons. They have nothing in common with each other. Except that they share the weak interaction, but they are really different species.
Do you count the gauge fields also, or fields also?
No, I'm sorry, I meant the matter fields. The gauge fields, we have 4 gauge fields. That's okay, thank you. So this is the Lagrangian at the moment. So let's see d mu, let me write the d mu piece, So I'm going to separate, let me separate inside TA, I will separate sigma 1 over 2, sigma 2 over 2, separately sigma 3 over 2, and y over 2. I will treat separately. Why? Because these are diagonal. This is by definition diagonal. Remember, it commutes with the gauge sp2 group. So that's what I mean, that hypercharge commutes with TA. It's just a number. Sigma 3 is diagonal. So we will treat them separately. For example, here, particle can mix sometimes when they carry the same charge. What I write down may not be eigenstate of mass, and usually it's not. And these, of course, sectors cannot talk to each other, you agree? So let's do this separately. Another thing to say, I didn't write the mass term, which normally we do. Why? Because the mass term is not allowed. We are really writing, we are following the prescription of a symmetry. We are trying to see how far it takes us. Okay? So, since the symmetry is postulating, we remember that the fermionic mass term, F bar F, breaks the symmetry between left and right, and therefore this can never be an invariant. Okay, so let's do the charge part first. Charged gauge boson. It will be clear what it means. These I call charge. The off-diagonal photo I call them charge because they will not have diagonal interaction. So I'm guessing that they are charged. It will be clear in the moment. So I will have I. And the only piece where it acts is on left-handed fields, right? So what I have is I, U bar, D bar, L, gamma mu, D mu. Well, I'm looking at interaction, not the kinetic energy. I and minus I is going to give me a plus sign, right? There is a minus I here. And there is plus I outside. So I will get G over 2. And then I will have 0, A1 minus I, A2, left. A1 plus I, A2, 0. You agree? I am isolating this piece. Okay? Just looking at the off-diagonal piece of my interaction. And you see what I guessed happens, these guys will mix. Now the state is not A1 or A2, it's a combination of them. We'll see in a moment, okay? This and then UDL. Where up can be up or it can be neutrino, it's the same. There is this confusing thing, up and down is a very convenient notation, it's true for any doublet. So sometimes we should keep it in mind when we write a generic SE2 interaction. It just tells us how up interacts with down. Just like spin, up and down. So what I get is, I'm going to write it like this, G over square root of 2, U bar L, gamma mu dl, A1 minus I A2 mu over square root of 2. So we sort of guessed that we had to work like that, and we even commented on this briefly in the very beginning, but now we are saying it nicely, explicitly. This is a messenger, obviously. This is the what we called a W boson. The guy, W boson, what it does, turns down quark into an up quark. Makes neutron become proton. This is beta decay. It makes, and this is why I look at the off-diagonal generators. And this particular combination, sigma 1 minus I sigma 2, is the generator that does this weak transformation. Changes flavor, we say. This is called flavor, up and down. Up, down, neutrino, electron, we call this flavor. As opposed to color. So color, only quarks have color, flavor everybody has. I put a square root of 2 just to normalize it the same way it was before. And this I should call W, what is it? W plus. Yes, charge plus 1. Right? So we'll keep this here. W mu plus minus is A1 minus plus I A2 over square root of 2. It's sort of a bit tricky, but you have to remember, plus has minus here. Anyway. Well, this was the first step. You know, we are constructing it in order to get a weak interaction. Okay, so we can't say, oh, we predicted something. That would be asking too much. We are now just, what we are doing, we are completing the Fermi theory. We often call it ultraviolet completion because it should be valid at high energy. And we are introducing the messenger. This is why I said it had to be SU2. We guessed that. This is the only thing which is kind of trivial, okay? We are getting out what we put The rest is sort of what will, be the success of the standard model. Everything else will follow. Okay, once I say that.
Shouldn't that be W minus?
Sorry?
Shouldn't that be W minus? Because you have an incoming down and it carries a charge of -1/3. You have an outgoing up which has a charge of +2/3.
Well, the Lagrangian carries 0 charge. This is -1/3. This is -2/3. Normally I'm reasonable and I agree with you guys. This time I have to insist.
But I was saying that this particular term represents the vertex where you have an incoming down and an outgoing up.
Okay.
So to conserve the charge at that vertex, shouldn't we have W minus?
Well, the charge must be 0
Yeah, from this
of the Lagrangian, that's for sure. So let's see, you are saying that the down quark is entering. Okay, let's make, that's not happy. Sorry. No, but I'm kidding, this is important, okay? You're right, you will see what confuses you. You're right and you're wrong. So up quark is going out. And then you are saying I should have, say what you meant.
I was saying that if a down quark is entering and an up quark is going, then if we assume that there is a
Right.
boson,
W minus should go out.
yeah,
Of
but
course.
incoming, okay. We have a
W minus is going out. This is very important. You are right. I could see what was confusing Hassan. He's right. W minus is going out, but it's equivalent. What you write here is what is entering into the vertex. So W plus is entering here. So that's another way of saying it, but that's equivalent to W minus going out. Right? This is the beauty of particle and antiparticle symmetry that we have in field theory. Right? This is how we should interpret Feynman diagrams always. So now I have a fundamental interaction. I have a charged messenger who is reproducing the weak interaction, and the fact that parity is broken, it interacts only with left-handed guy. This is maximum. I mean, if you interact equally with left and right, then parity is conserved. If you interact only with left, if I have not only half of my body, that's maximum. This is almost maximum. If my heart was in the middle, it would be symmetric. Okay, so we have sort of variations. And it's I can't overemphasize that. It's all based on the parity violation being maximal. The fact that we can construct the theory in a simple Higgs manner, you will see. It will be much more messier. In other words, the weak interaction W plus could have been U bar A plus B gamma 5 gamma mu D. When B is 0, I have maximal symmetry. No, we live in the world which A is equal B equal 1, something like this. But B could have been 0. Then we will have a parity conservative theory. We'll talk about that world. Or we could have, A1 and B 0.5 and so on, okay? Then what would I do, right? It would be very hard. So what is the right-handed guy? It's a little bit of a doublet, a little bit of a singlet. You see, for constructing the theory, it's extremely important that either parity is maximally broken or it's not broken at all. You will see when it's not broken at all, the world that everybody loved until 1956, the summer. Everybody was sure forever that the world was left-right symmetric. Even Li and Yang, if you look at their fundamental paper, look at the page 4, they say, well, we are suggesting parity violation, but we are sure that the fundamental theory of nature eventually will be left-right symmetric. It's interesting. Now, how do I reproduce weak interactions? I'm sure you've done this it's Smirnov. You say precisely what, so let's do it. Let's look at the, for example, the beta decay. For us, that's down quark decaying. So down quark is heavier, remember that. Neutron is heavier, so down quark is a little heavier than the up quark. That emits now. Now I want to look this way. This will emit W minus, right? And if I emit W minus, what I will get here is an electron coming out. Conservation of charge. A neutrino is entering. But that's equivalent to anti-neutrino going out. This is my beta decay. Do you agree? So how would this look like? This would look like at every vertex I have g over square root of 2, so I will have g square over 2, this interaction. And then I will have UL bar, gamma mu dl, EL bar, gamma nu, nu L, and then I have a propagate, which is g mu nu minus k nu over mw square. Well, I'm imagining that W has a mass, obviously has a mass. At this point, it's still massless. Okay, but let's worry about that later. I want to be sure that this messenger can give me correctly weak interactions. Then I will have to understand. And I want to get a Fermi theory. Now, Fermi theory was an effective theory that he wrote down at very low energies. When you say very low energies, then you mean very low energies, okay? Its k is much smaller than mw. Well, that's what you mean. You take the limit k going to 0, basically. You take the leading term, right? So I can get rid of this. Notice that if the energy is not small, if I go to the energy is much bigger than mw, obviously the idea of weak interaction breaks down completely. This is the beauty of a messenger. You can't speak of weakness of interaction, depends where you're looking. At very high energy, W is like a photon, almost. But at low energies I get this, and this is a famous interaction. What I get is g squared over 2. I can just write like this, 1 over mw squared. And this I could write as a current, weak current times weak current bar. No, let me write it nicely, completely. Let's write it here. This becomes g squared over 2 ul bar mw squared ul bar gamma mu dl el bar gamma mu nu L. This is the interaction Fermi would have written. Only he would have called this 4 g Fermi over square root of 2. The 4 is because I have a half hidden here. Fermi would not have written it. He didn't imagine a left-handed interaction. He imagined sort of an interaction which would be similar to the photon one, just the current interaction. But he was aware that in general you could have anything. So when people took Fermi theory seriously, they wrote all possible interactions. Vector times vector, vector times axial vector, scalar times scalar, and it took a long time, 20 years, to untangle the form that we sort of just write like this. So you see, now important statement here. So let me write down the famous standard model interaction G Fermi over square root of 2 is G squared over 8 mW squared. When people discuss the Higgs sector, the Higgs mechanism that we talk about, people often say, almost everybody I know, that sort of the problem with the Higgs that you cannot predict the Higgs mass. You cannot predict W mass. Notice here that sometimes you think that you can. It seems you have measured this, but you have no idea what G is. So it's not true. And this is the reason before the standard model emerged. The people didn't speak very much of W. I mean, they would imagine it and so on, but you couldn't say anything because the smaller G is the lighter W, the bigger G, the heavier W. So you had no way of knowing where it would be lying. Right? So MW, not predicted. Not from here, not by itself. And this is a typical situation. Masses are not predicted. When we have a good theory, we relate them to something else. Okay, you will see that we will achieve. Awesome.
Why did the currents do?
Sorry?
The currents do L, comma mu, dn.
Yeah, they should follow GF, but he didn't write it.
The two
So
currents
he's assuming that you have written all the expression as 4 GF over under root 2, but there are currents. You didn't write it.
Oh. Thank you, sure. I'm sorry. I remember I was giving a talk. It was actually in Austin. There was Weinberg and other people. It was a little embarrassing because I was very excited. I said, this is the particular effective there. There was nothing written there. It was worse than here. At least you could say maybe it's the line above, but I somehow, it was left in the other transparency, in the other slide. Right, all I'm saying, well, it's here, right, the magic formula. If you want to make a prediction for W, we have to find a way of measuring, of knowing what G is. But when I'm at low energies, all I can do is say that I can't be wrong yet. Okay, Pauli would be telling me, okay, not even wrong. Now, of course, as I go to higher energies, I can have a way of directly measuring the interaction and finding what G is. That's a different story. Okay, so let's see what the neutral part does. Something should be raised. Let me try if I can. Let me try to see if I can. So this was a charge part, and this is now the neutral part. The neutral part, notice, since they are diagonal, what I'm going to have, I can just write generically F bar. I'm picking up an interaction from here. So I'm going to have GA3 T3 plus G prime. And now I have to think. Now I have this y over 2. What in the world is y over 2? I should have said it earlier, but better late than never. The meaning of SU2 cross U1 theory, when I say that this is my effective gauge symmetry, what I mean here, that it will describe the real world, electroweak, I said, therefore photon has to be inside this. Therefore charge must live inside the group. Therefore, it must be a linear combination of T3 plus y over 2. I could put some coefficients here, but this is completely arbitrary, so it's not necessary. I can reproduce all the charges. So you see how this formula works. Actually, the way you should think of it, this is the way to think about it. Because you know immediately what T3 is. I specified everything for you. Here, you agree? So, for example, if I ask you what is the hypercharge of the UR, right-handed quark? What is it?
Electrical charge minus 2.
Right? So what is it? T3 is 0. So it's just 4/3. It's twice. And dr would be minus 2/3. Hypercharge is twice the charge for the right-handed guy. And if I ask you, I don't want to write dr, let me just try one. What is the hypercharge of a left-handed neutrino? It's twice, charge is 0, minus a half. It's minus 1. For example, quickly, what is the charge of the left-handed electron? Huh? No. This means that they must have the same hypercharge. When you commute, what does it mean that they commute? Lorentz symmetry commutes with this. When I tell you that the Lorentz symmetry commutes with this, it tells you that up and down must have the same Lorentz properties. Otherwise, I would break the Lorentz group. For example, if I tell you that this commutes with color, then up and down must have the same color. I cannot put the red up quark and the yellow down quark. So if I tell you that the hypercharge commutes with SU2, that these guys carry the same hypercharge, I don't have to do the calculation, okay? And the way, of course, it works, it will be twice, and charge will be minus 1 plus a half. This is minus 1, and so on and so forth. So the trick here is all to remember that you should write I can put the mu index here with gamma mu, but it's irrelevant. I could even get rid of it. Sometimes to get a form, you can forget that this guy carried, the gauge boson carried the Lorentz index. It's irrelevant for the form of the SE2 interaction. I mean, SE2 interaction is looking at internal property. That commutes with Lorentz group. So I can, when I'm lazy or when I want to see, quickly, I'm tired, I can just ignore it. So let's ignore it and stick it back later. So look, this will be F bar. Let me take these pieces. I have G, A3, minus G prime B times T3, you agree? Plus G prime Q B mu B. I can put mu outside. This will be true for any fermion. You see what I'm doing here? I don't have to write the specific thing that I needed when I was looking at the off-diagonal interaction. By the way, I think I will have to erase this one. It's a portion. Why don't I have to worry whether it's a doublet and a singlet because it's hidden here? I've already memorized it. If I have a singlet, I'll put E3 equals 0. If it's a doublet, I'll put whatever. For upper component, I'll put a half. See, so I can write a generic formula for any fermion. That's the beauty of group theory, you agree? Now notice, I had fields A3 and B to start with. But now I can see they are not going to be physical fields. I see immediately, for example, this cannot be the photon. Photon couples only to charge. So this guy is something else. We call it Z boson. It's identically GA3 minus G prime B, and we normalize it. Put a mu index if you wish. I got it immediately. See, this is the beauty. By the way, this is very important, okay? Often this is not the way, in the books it's not portrayed the way it should be. It's associated with the Higgs mechanism. So this is derived later on when people actually studied the, Weinberg-Salam completion of the glacier. We are not talking about how these particles are getting a mass. I'm just showing you how the very structure of SU2 cross U1 gives you interactions. This is a glacier 1961 paper, if you wish. Made it transparent. It's not so, that paper maybe is not so clear as the Weinberg paper. Well, I'll send it to you, you can judge it. That means that there must be another particle, of course, which is orthogonal to Z. That must be the photon. I have only another possibility. If I'm okay, it should come out to be my photon. Otherwise, I failed. It must be orthogonal to this. Right? I started with A3 and B, now I'm creating independent orthonormal states out of those. So this should be G prime A3 plus GB over square root of G squared plus G prime squared. This is my neutral interaction, often called neutral current interaction. Maybe we should put it somewhere else. So therefore we get neutral current piece will be F bar. Okay, so this piece is the Z. Okay, F bar, gamma mu. Why don't I put, there will be a square root of G squared plus G prime squared F bar gamma mu Z mu T3 F, the first piece. You agree? Here. A and B. Let's keep the track so that this is A piece. Plus, then I have G prime, Q. Okay, I'll take this out. What I have is G prime Q, B. What is B? B is G B is G A mu divided by G square root, but I took the square root out, so I will have this. You see this? Actually, I don't like it. Am I doing something wrong? Yeah, why am I doing this stupid thing? Let me keep it. I'm sorry. It's not fair. I would confuse myself if I... This is the A piece. I'm now writing what B is. B depends as G A mu minus, there is G prime Q, and then G prime, it's normalized G square plus G prime square, Z mu times F. Okay? I have Z and the function of A and mu, you know how this is. This is a rotation, right? Do you recognize that this is a rotation?
For mu, is it G prime A3 or G A3?
Sorry?
For the one for mu,
Yes.
the G and G prime should be left there, don't we?
I'm not sure what you mean.
Should it be G A3 plus G prime?
No, GA3 I have already. It has to be a orthogonal. This form is fixed. See, this is beautiful. If you know A, you know Z, and vice versa. There is a unique prediction of the standard model. The existence of the photon. I'm assuming that there is a photon, so I'm saying I have to describe the photon, that this guy cannot be the photon. I cannot, of course, get everything out without having an input. So I have to say I'm constructing a new theory beyond QED. It has to contain QED. So I'm Glesher in 1961, and I say there must be a photon in the theory. That's what my theory is all about. Therefore, this guy here is not a photon. But the photon will have to be coupled. And you see, it's working nicely. This is my photon. It's coupling to charge. Notice what I've done here. This is a rotation. Introduce the following angle. Tangent theta W is G prime over G. The weak mixing angle. There was a time when it was called Weinberg angle, funnily enough. Did you check the paper that I sent you? Weinberg doesn't have Weinberg's angle. He doesn't have the weak angle. The weak angle was introduced by Gleshow, but I think it was pi over 2 minus this particular one. Later on, 3-4 years later, Weinberg introduced weak mixing angle, but it's a weak mixing angle, nothing to do with. Anyway, it would be trivial to give it a name. It's just because I recognize it's a cosine in science. So when you have the rotation, you know how to read off in the other direction. You will get the same coefficients. This is very important. Okay, check it, please. I'm reading off from here. I'm saying V is G A mu. It will depend the same way. This is sort of how you entangle the rotation. And it depends on Z with the minus G prime. So what I reproduced, the Noether current interaction. So this, by the way, G prime, G over square root of G square plus G prime square. This is called electromagnetic charge. Which is, notice, this is G sine theta W. Psi theta W is G prime over the square root. And cosine theta W is G over the square root. So you see, the existence of photon uniquely fixes the existence of a new gauge boson. Okay, this is the beauty of the minimality that gave us this structural prediction. I get here, I get E, F bar, gamma mu, Q, A mu F. This will reproduce QED. Right? This I call E, because this is E. And then I get, notice that I have a square root of G squared. The Noether current has a sort of bigger coefficient. This I can write G over cosine theta W. Do you see this? This is G over cosine theta W. Okay? I'll take it out, and then I get F bar, and then I get T3 minus, there will be Q, and the Q goes with G prime square, so we will get sine squared theta W. Do you see this? I don't need so many brackets. Do you see this? This is E. I took square root of G squared plus G prime squared. So I will get here G prime squared over G squared plus G prime squared. I took the square root. This is what I call sine squared theta W. So there is a universal form for the photon assumed. We will see that with the Higgs mechanism we can do better than this, okay? But since I don't really know, you see, I don't even know how to identify the photon. At this point, everybody is massless. So I have to say the way Glashow spoke. Says, I don't know what to do now. But I believe there will be a mechanism to give Z boson the mass. I know it has to have a mass. We don't see it. It's better be quite massive. What I can do for you already in 1961, even before knowing how to break the symmetry, I can predict, if you believe in a gauge structure, I can predict the form. See, the Z current is also of a general fundamental form. Whereas the photon couples only to charge, Z boson is not so selective. It couples to charge too, but it couples also to T3. Notice that because of this, I can write the thing as E squared over sine squared theta W. Right? E is G sine theta W. Notice that weak interactions are stronger than electromagnetic. It's really a lousy name, you know, today. But it had to be chosen because at low energies, when they were doing their experiment, weak interactions are very weak, but they are stronger than electromagnetic. How much stronger depends on the value of theta W, but without anything we know that this is that sine theta W is less than 1. So what we could, you see what the standard model predicts. Not the mass of W, but it correlates it to this parameter which you can measure. You see now what Gletscher achieves, okay, which is beautiful. Gives you a universal form of neutral currents. Now you can do a neutral current scattering. You can scatter neutrino on an up quark, scatter it on a down quark, scatter it on a deuteron, scattering whatever you want. You can now imagine millions of different experiments. Electron on a anti-electron, electron on a muon. There are more generations, okay, pretending. And I have a universal form, okay, so this is the beauty of the standard model. You know, I have, in the weak interaction sector, I have just one parameter, which is theta W. So you measure theta W from here. That's what they did. Of course, you may tell me, I don't know the mass of the Z boson, I don't know the strength. Doesn't matter. You can look at the branching ratios. Remember, when you have many different processes, you don't need to know the strength. You can just look at the relative strength between two scatterings. Neutrino on up quark divided by scattering on a down quark. On a deuteron, on a neutron, on a proton, the strengths will cancel. So even I could be very naive here. I would say, well, somehow I'm sorry, I'm Gletscher, forgive me. I believe that there is symmetry and symmetry will stay at high energies. I also have to break it. So Gletscher says, okay, I add electron mass or whoever and the Z boson mass. I don't know how. It's just a parameter for me. But what I want to tell you, even without anything sophisticated that we need to introduce, we need a Higgs mechanism because this doesn't work. Why? I cannot do loops. I cannot do perturbation theory. The W propagator is bad. It's a propagator, but I want you to see that there is a striking predictions. This was measured, by the way, theta W is roughly 30 degrees. That you should remember. Sine squared theta W. I don't know if you remember it. It's almost a quarter. So, you know, sometimes just when you want to see quickly what is going, put a quarter there. Put 30 degrees, some numbers may become zeros, then you have a quick thing. So you see from here, once I know theta W, I know GF, I know E squared. So this is my fundamental relation. Let's write it here. G Fermi over square root of 2 is, what is it? E squared is what? It's 4 pi alpha over, I have 8 there, right? 8 mw sine theta w squared. So let's write this formula. A mu is sine theta w, A3 plus cosine theta w, V. And Z mu is what? It's cosine theta w minus sine theta w, the other guy. These are the physical states. This guy is apparently massless. Well, I can't say anything about that.
But
And this guy apparently is massive. I cannot say anything about that. It's just...
by physical, do we mean that they are eigenstates of the Hamilton?
Physical, right. The simplest way to say that they are eigenstates of mass. When I have two states with the same properties, spin, charge, everything, then they can mix, and they normally do. There was also mixing here. A1 and A2 were mixed. The physical state is not A1 or A2. It's a linear combination which carries charge. It would be silly for me to work with A1, A2. I can, but it would be silly because I don't see the charge nicely. So I like to have eigenstates that I can read of their properties. In this case, I must postulate that MA is 0. In this case, I must postulate MZ, whatever experimental. But just to appreciate that what people found very exciting, that I can now write that MW sine theta W is square root of 2 So I will get that MW sine theta W is pi alpha electromagnetic divided by square root of 2G Fermi. I think this is correct. Check if I'm right. I can predict MW if you tell me what sine theta W is. I did achieve something. I related the mass, which is an arbitrary parameter normally, to a dynamical quantity, which is the strength of interaction. Okay, that is nice. This number was people notice it was 40 GeV. No, it's not. Well, this number. This is the input, roughly 40 GeV. So when sine theta W is a half, you get MW is 80 GeV. When sine theta W is roughly half. This is the famous prediction of the standard model that was verified in 1983 when they found the W. It agreed beautifully with the predictions from the. Another thing that I will show you in the Higgs case, we can actually predict the Z mass. Now it's arbitrary. But okay, first things first.
So all of the analysis that you were doing were for the diagonal parts, D3 and.
Right. Well, I did the charge part separately.
Yeah, it's the charge part.
So
is that the only reason because of which we don't, they were changing neutral currents cannot be in standard model? Because if they were changing mean that you will have to have off diagonal entries there.
Oh, but I cannot speak of flavor. It's a little early. I have only one generation, so there is no.
For example,
You're worried about down quark becoming strange quark, but I don't have a strange quark here.
Okay.
No, we'll talk about that. That's a profound subject. I know you've heard it. I will sort of rediscuss it to try to have you capture what you're asking. It's not obvious here that, well, it should be obvious. Okay. Now you are telling me, well, this is what we can do, knowing that there are more generations. You say, when you put generations, I don't know, maybe there are 15 generations, are they going to mix? Then you say the following, look, in the case of the photon, they don't mix. That you know, right? This is the essence of the way the photon interacts. It takes you and keeps you forever. It cannot make Yasser become Hassan ever. The electron stays electron. Now this is of the same form. You can prove immediately if this is flavored diagonal, we say, this will also be. That doesn't mean that this has to be flavored diagonal because it's a completely different species that we have to rediscuss. But one thing I can be sure of here, that Z boson is really just like another photon, only massive. For all practical purposes, they are the same. Little difference here in the couplet.
So we can have charged flavor changing currents but not neutral.
But not neutral flavor changing current. Not at the tree level, not in the Lagrangian. When you do loops, you never know what will happen. But you may even generate neutral, okay. Nothing forbids things to appear in higher orders. The beauty of the renormalizability means that if they appear in higher orders, you can compute them. There will be no famous infinities, so-called. And we'll do at least one such calculation. It's nice that you see how infinities cancel.
When you're talking about the whole process, I'm asking about a single vertex. And a vertex, you cannot have flavor changing and a neutral both are limited.
True, but I'm also talking about the vertex. Z boson cannot change flavor, but I can exchange a loop and then you can have it. Whatever we say is a tree level. All
three vertices.
Right, at the tree level. But it's still a vertex, so when I say loops can change whatever we. So if the Z boson, for example, has flavor conservation here, loop may change that. A priori, I don't know. But it's a Seidelmann. But just to remind you, whatever we conclude at the tree level, we have to rethink. So when we want to know whether or not it happens at the loop level, we have to use symmetries as an argument, but not, if maybe there is some symmetry that forbids it, then it will never appear. But if the symmetry does not forbid it, typically loop will violate what you write down. But, okay, sorry, I'm getting ahead of myself.
Doesn't supersymmetry predicts
symmetry?
Yeah,
Supersymmetry.
I'm wondering because, as you say, we haven't seen any flavor change in neutral currents, but I think it does predict. So how people avoid this? People that work on supersymmetry.
But standard model also gives you flavor change, you know, that kind of. No, all I'm saying is you don't get it at the tree level.
But at tree level can be.
No, but then you do it and well, I don't know how to answer the question on supersymmetry because we don't really know what supersymmetry is.
Yeah.
Well, it's a symmetry in which I imagine, as Gleshow puts it nicely, it's a fantastically tested theory. We already found half of the predicted particles. Gleshow has another thing that he said recently. He was reviewing a book that he didn't like very much, but he was much more polite than I would have been. So Gleshow says, there are many people that come to him and say that they don't like standard model, they find some faults. I also find some faults, I admit. Of course it's true, who cares that I find faults, right? But then they come and tell me that they like supersymmetric standard model. And I told this to someone and he realized immediately, I don't know if you guessed it, you know, he started to laugh immediately. You understand, that's being stupid. Supersymmetric standard model is just standard model with 100 more parameters. But it has the same ugliness or beauty, whether you like it or not, you decide. But you can't dislike standard model and like supersymmetric standard model, that you're not allowed to have. Because it's the same thing, basically, just sort of double. You know, supersymmetry is a little, now that you ask, so a little thing for those of you who are not so familiar. I know everybody now will tell me this is trivial. But anyway, it says if there is a proton, there is a proton. So there is circuit, there is, it becomes complicated. The language becomes, you know, you know. So electron has this electron and so on. So these things that people say that usually these statements are actually not, they're nonsense. And I'll show you in a few examples how actually when you do have a theory beyond the standard model, these so-called constraints, for example, no flavor violation, actually are not a problem. I would say they are a blessing because they restrict your parameter space. And well, we will come back to this question because it's not well taught normally. Remember what we said today. We'll come back to the way flavor conservation works in the standard model. It has to do with the famous G mechanism that you learned before coming here, but I will make you sort of maybe appreciate in the context. Now we are sort of building upon what Alexei did, right? We are making it now more rigorous in the context of the gauge structure. So it's good to re-see again the things we've seen before. Well, so far so good, we would say. But the bloody problem that was bugging me from the beginning remains. W, if I stop here, I have a massive gauge field, and I don't know how to work with that, whether it's W or Z, right? So we have to do the Higgs mechanism. The next step is Zacharias.
Can we still use this for high energy processes? See like very boson as massless particles?
Yeah, sure, at high energies. This is in a sense what Glashow, another, we can say for Glashow, was not completely stupid. Why he writes this theory? He knows that he has to break the symmetry. Because the electron has a mass, and we didn't write its mass. Quark has a mass, and worse, W has a big mass, and we didn't write it. So you can ask him, and he's like, why am I writing a theory, imagining a symmetry that I have to break? Because the hope is, when you break it in the mass term, as you go to higher energies, as Zacharias is commenting, then this should become irrelevant. And therefore, the symmetry may once again be important, although I broke it. For example, if I go to the energy much above electron mass, and I compute W decay into an electron and anti-neutrino, I can really use the symmetric interaction because it's irrelevant that the electron is massive. And I can see it also when I write the electron propagator, it's 1 over p slash minus m. So when I go to very high p, this becomes irrelevant. Whether I think of it as a free, explicitly on-shell state or a virtual propagating, that's a good reasoning. Glashow also knew that he had a problem. And the problem was a W boson, or a Z boson, because the propagator had these speeds that I ignored. G mu minus K mu over MW squared. This is not true. Here the limit going to 0 is not a good limit. So this is where he got stuck. But it's thank God that he wrote his paper, because you see someone else comes and cures the problem. As far as the electron goes, we could have even written the theory and left it as it is, but we cannot do it for the W. So once again, I insist that we must do the Higgs mechanism. Okay, this is beautiful. I want to show you that this is one of a really beautiful examples of a theory. The standard model made predictions at each stage ahead of experiment. This is rare. Usually you have the mixture of the two. Not in the case of the standard model. Everything was predicted. Like, for example, the form of the Noether currents. If they had read his paper carefully, which nobody did, some people who had gotten a Nobel Prize in the 60s, there was a graduate student in the, I think it was Gargamel, one of these experiments, that saw Noether currents, and he was hushed. Now, because people didn't, when you don't know that you should see something, you don't see it.
Why do you think that?
I don't know if there was something with my daughter. I have to ask her whether she thought of this or someone else said it. Normally you say that you have to see something to believe it, right? It's actually a little careless statement. You have to believe also to see it. If you don't believe, you won't see it. People didn't believe that it should be there. In 1929, there was a graduate student at Caltech who was seeing a positron, but he didn't believe it. So nobody saw it. They could have looked at his data. He stopped seeing it. You start outing yourself. So there is this tricky thing to have in mind. Now, Glashow's paper is not so easy to really, maybe not easiest paper to read, but it's still fairly clear. I find it very strange, and I often ask myself, would I have recognized that?
You just said that in the case of standard model, the predictions were made way before they were.
Yeah, it was made in 1961, but they didn't take it seriously. Many, many years later, only in the 70s, People, just because it Hoff came and showed it that the theory is much deeper, much more complete that you could actually compute once you implement the Higgs mechanism. So now this is Weinberg, Salam's work, or precisely, you know, Weinberg's 1967 paper is particularly clear. Oh, I should have left some of the things. We have to reproduce them, but you remember them now. The one thing that I shouldn't ever read is T3 plus Y over 2. Remember sort of thing, there is one thing, you know, when you look at the standard model today, the things that may bug you, this always bugged me. I saw it first. I tell you the calculation I did when I finished this in 1974. But it sort of bugged me that the world is so sort of asymmetric. Doesn't matter. Another thing that is sort of unpleasant, that you can never remember this hypercharge. I think I remember it probably now, but often I have to go back. Right? It's sort of, you do remember the charges, you have to remember, you know, it shouldn't happen now that you finish here and you don't remember up and down walk charges, okay, the others, you know. And T3. Oh, okay, I'll come to it when I do later. So the Higgs, so we said, let's do the Higgs. After all, we studied it for some weeks. Spontaneous symmetry breaking. So what Higgs should I use? I have no choice. This is nice. Define Weinberg, 1967. It's a nice story. Weinberg says that, you know, Weinberg, if you look at his work, he likes to do very complete, profound calculations, not just original things. You know, look at his work. This paper stands out. It's not Weinberg-esque. And the reason, he says he was very unsettled. They moved from one place to another. And his wife was working, and he had a little daughter that he had to take to playgrounds because they didn't have a school or a babysitter, so he couldn't do his calculations. I just do that. I try to encourage my younger collaborator always. I'm a cafe physicist, to go out of your office. Remember that. It's good, often, to just walk out and stare at things when you cannot compute. He couldn't compute, he wrote this, what I'm writing now, and he made history. So what should be the Higgs?
It should be a scalar.
Okay, so my Higgs is, let's start, I, scalar, good. What about the properties under SU2 and U1? For example, under SU2, it is SU2 L, what? I can take quintet, triplet, doublet. I know everything. Why doublet?
Yukawa interaction.
Yukawa interaction, precisely. This is what you asked me when we did SU2. What Sergio asked me, you know, but what are we going to do about fermions? And you see what I have to do about fermions. So the catch is here. Of course, I'm doing the Higgs mechanism because I want to give gauge boson a mass. Now I took it very seriously, my idea of spontaneous symmetry breaking. I have to give everybody a mass. I cannot now do explicit breaking and spontaneous breaking, okay? They won't work. So it's easier for me first to look at the fermions because their masses I know. I don't know anything about W and Z masses. So you say, aha, I cannot write, it's true, my mass. I wanted to write QL, dr, for example, but I couldn't. This is not symmetric. So it will be only symmetric if I put some doublet, some scalar here. And the scalar, obviously, is a doublet. It's done. This is an anti-doublet, this is a doublet. This is trivial. We will call this Yukawa down. For obvious reasons. Okay, now I go. But I want to do this for the up walk also. Yukawa up, 5, you are. Can this work? Yes or no? this works for sure. That's a definition of phi. I can't fail here. Now, once I define it, I can fail now. Why? Because dr and ur do not have the same hypercharge. If this is invariant, this cannot be. Actually, let's compute it. What is the hypercharge of dr? Yeah, it's terrible if you say, if you like, you know, this may sometimes look confusing when you say I like to work on fundamental issues. Why sometimes you think the formalism is more fundamental? You don't have to deal with numbers. So you don't really have to deal with numbers. It just helps. I could do this without numbers because I can connect the hypercharge of ur and dr. They have to have the same charge, the same. I know the charge difference. I'm sorry. I know that the charge of ur is the charge of dr plus 1. This I know. Right? Proton has neutron charge plus 1. I know that the charge, that's enough to me to know that if this is true, this cannot be true. There is a difference of a charge. And just to see how it works, this actually QL, what's the hypercharge of QL? 1/3. Good. It's true. Well, let me give you a little trick for a doublet, how you can remember. Take a doublet and do the following in a doublet. The sum of the charges, there are two particles in a doublet. Q up plus Q down. The sum of charges is, sum of T3 is 0. Plus y/2 plus y/2. That's y. So it should be easy to remember. Y is just the sum of the charges in a doublet, which is 2/3 minus 1/3 is 1/3. So phi has a hypercharge plus 1. This has minus 1/3. This has 4/3. So this guy has minus 1. So it's not phi. So who is it? Phi star. A phi star is not a doublet.
Phi bar.
No bar. Okay. Well, phi bar, if you define what you mean by phi bar, no, it's okay. No, he can say phi bar, but he has to define what he means by phi bar. For example, psi bar is psi dagger gamma 0. No, it's true. You can write the phi bar if you tell me what phi bar is.
It cannot be phi bar, obviously, because then Lagrange.
No, depends what you mean by phi bar. Phi bar you have to define, it's a scalar.
Then it's like the charge conjugated, but in the hypercharge, not that.
Right. Well, this is what we said about SU2. I wanted you to have it in your fingers. I said, you must always remember, how do you get spin 0? By I sigma 2. I sigma 2 is a magic thing that takes a spin into an anti-spin, if you wish, or gives you a spin 0. For example, if you have two doublets, doublet 1 transpose I sigma 2, doublet 2, this is spin 0 state. Up, down, minus down, up. So here, if you transform correctly, if you multiply by I sigma 2, you can call this phi bar if you like. People actually call it phi tilde because bar is reserved for. This is SU2 invariant, that's easy to check. So it's nice, it's fitting, right? This is one of those things when magic happens, okay? I I still don't understand. He wrote this paper, but he didn't pursue it afterwards. He didn't write more papers on that. This is interesting, but it is sort of something that you get goosebumps when things start to work. Then you say, well, we have to do it. Let's not get so excited. We have to do it for the electron. There will be permission conjugate. Well, this guy has hypercharge -2 because it has charge -1. We found this one has -1, so this is +1. So this works beautifully. It's fine. So one and the same Higgs. Now it's going to give me all the fermion masses. Okay, this is beautiful. Okay, I will repeat it. If you tell me that there are more generations, okay, I know how to zero copy. Okay, I just go there and copy. So that's going to be easy. So we could be on the right track. So this is the same example that we took with SU2. We did SU2. Here, of course, it's SU2 + 1, so it's the same doublet that you and I studied just a week ago, or maybe 5 days ago. The only difference it also carries hypercharge. That's okay. And charge is T3 + y/2. So phi you can write immediately. Can you tell me what will be the upper component charge? This is the hypercharge. So what will the charges be?
1.
Half plus a half is 1, and 0. With my conventions. Now I've chosen some conventions, obviously. Everything is now a convention that I'm going to follow. So in my convention, the lower component is neutral. So in other words, with my connection, the vacuum excitation value of phi would be this one. That we wrote as 1/√2, remember? The only thing is, if I look at I want to see how much symmetry is broken before doing calculations. So I have TA acting on phi 0. Phi or phi 0. This is non-zero, you agree? Also hypercharge acting on phi 0 is non-zero. I broke everything. Oh. What's wrong? I should get a photon. Charge is not supposed to be broken. The way I took it, it seems that all 4 generators are broken. If the generators are broken, we know a theorem. You and I proved the theorem. Every time we break a generator, we get a massive gauge field. 4 broken generators, 4 massive gauge fields. W+, W-, Z, and photon. So it seems it's going to come out wrong. I don't want to do the calculation yet. I'm just trying to check before doing the calculations. Like also, if the breaking is okay, we'll see how we get the mass and so on. But we'll do that. Well, the point is that
we can mix the fields to get a mass level.
Fields. Well, fields comes later. I'm just studying the symmetry breaking through, and I know that we mix them. Yes. Yes, we do. Precisely. There is a mixing. This is correct. However, here among this TA, there is sigma 1, sigma 2, there is sigma 3. The sigma 3 and Y are special. They are diagonal. So, I'm giving you a hint. I just want you to say it. I can take any linear combination of these guys. They are as good as the For example, this particular linear combination is very interesting. So I look active Q electromagnetic 150, which is sigma 3 over 2 plus a half. Hypercharge is 1 acting on 50. What do I get? One linear combination is unbroken. So this is a prediction now in the standard model. Glashow had to assume that there is unbroken charge. You and I are predicting it. In the minimal standard model, charge is unbroken, period. And the photon will have to come out massless, period. Not a little mass, massless, okay? We are doing, now we are going beyond Glashow. We are already achieving more than him. We find the common source of all the masses. This is very interesting, okay? This will give us interesting predictions of even before doing any calculation. The other important thing, by the way, you could have guessed, you have one field and you have two Cartan elements. One linear combination you can always keep unbroken. You will always find it. Of course, it may look that because I took it in this direction, that don't get misled. If you take it in the other direction, there's just opposite definition of charge. Then I can put minus y over 2 and so on. But you can say, what if I put it in both directions? Well, that's another terrible redefinition of charge. I will have to say not T3, but T1 plus, with some coefficient, plus T2 plus T3. One linear combination will always be unbroken.
So we can say that what we are doing is that select a linear combination such that one of the diagonal entry goes to 0.
Precise. And I know this is the most general case because I can always rotate, so I don't have to worry that if I choose a different vacuum, I'll get different physics. It may be hard. We could even do it for homework. You say no, okay? A disbeliever says, no, you prove to me that you get an unbroken charge. Then prove to yourself. This is a neat thing. Find the linear combination. Now Q electromagnetic is going to be A1 T1 plus I don't know with what coefficient. With some. But it has to be. Why? Because I can choose vacuum in this direction. That's like choosing the z-axis. I can't be wrong. And I, of course, don't want to do lengthy calculations, so I. No, we can do it on Wednesday systematically. We sort of see that it seems it's going to work. There is just one unbroken generator. There is one web. So see what is going to happen. I have only one web, and it will give mass to everybody. So I'm going to get correlations, obvious. In other words, I will get correlations between MW, MZ, and so on. Even the fermion masses and their couplings, okay? They must, because they come from one and the same dimension full parameter. Okay. This is the magic. And this magic should be appreciated, okay? And we'll do sort of an example of another world of SU2 cross U1 so that you really see a miracle took place. When you go beyond the standard model, you run into a complicated Higgs structure that you can't avoid. But Weinberg is just thought of perfectly, okay? That one Higgs was sufficient. It's very surprising. Okay, we'll do it. Now on Wednesday we'll actually introduce the doublet, do the symmetry breaking, but I wanted us to anticipate. I wanted to whet your imagination that we could guess what was going to happen.
So when we go beyond the standard model, can we include charged Higgs electrically charged?
Well, there is even in the first glance you could say that even in the standard model there is a charged Higgs. You could say it's here, right? However, it's actually not there, right? Why? Oh, you do. We said, remember, that there is only one physical guy. The boson eat, and W has to eat someone. W carries charge. W will eat the guy who is charged. Charge is not broken, so if you're charged, you eat someone. You can eat only what your symmetry allows you. And the Z boson, you see there are 4 fields here. Remember how we said R1 plus IR2, R3 plus IR4? These will give me my G plus minus. W eats, this is G of the Z boson, the Z eats, that you should know. There is just Higgs. That's why we talk only about the Higgs, because we are lucky here. If you introduce 2 doublets, you have a charged Higgs, and you have to worry, will that charged Higgs get the web or not? So yes, in any theory beyond the standard model, the first thing you have to address to make sure that your charge field doesn't get away. Why didn't have to worry about that at all? Nothing of all the problems, okay? There is nothing else to worry about, okay? Anything else that we do, you know, it's always like that. The first, you have a great idea, there, obviously. You won't have much to compute. Okay. I stopped, so just if there are questions. Then. 1, 2, 3, no.